Hi guys, well done for logging on and finding the lesson. For those of you that don't know me, my name's Mr. Davis. I'm one of the science teachers at the St. Leonard's Academy, and I'm going to be giving you a lesson today about acids and alkalis and how we can determine the pH of a substance. So before we get underway, guys, just so that you're aware, for this lesson you are going to need a pen or a pencil, a notebook or a piece of paper, and a calculator. You're going to need all of those bits of kit if you can. You can use the phone for a calculator, but if you haven't got that stuff together now, guys, what I suggest you do is pause the video, charge off, go find all the bits and pieces you're going to need to be able to engage with this lesson, and then get yourself back on, press play on the video, and we'll be able to run on from there. Okay, go. Well done then, guys. Hopefully you've got everything you need now. So pen, pencil, notebook, paper, and a calculator, and we can get on with the lesson. Okay, so what we've got on the screen initially is a quick quiz. And this is just really to give you a chance to see if you can pick your brains over some of the stuff that you will have been learning in years 7, 8, and 9, and just give you a bit of a recap over your previous learning. So what I'll need you to do, guys, is just pause the video. There's only 5 questions there, so give yourselves 5 minutes at it and have a go at answering those questions. And once you've had a go at them, come back to the video and we'll go through the answers after you've had a go. Okay, guys, well done for having a go at those questions. I hope you didn't find them too hard. We're going to quickly now go through the answers for them. Where's my mouse gone? Okay, bang. There we go. Quick quiz and answers. Quick quiz answers. That's what I was looking for. Okay, so the question number 1, how might we find out the pH of an acid or an alkali? Well, initially we could use universal indicator. This is an indicator that changes color depending on the pH of a solution. Now, what is the pH of a neutral solution? That will be 7. An example of a neutral solution would be water. Which of these is an acid? Vinegar, toothpaste, or blood? In this instance, it is vinegar. Vinegar can also be called acetic acid. And which of these is an alkali? Vinegar, toothpaste, or blood? In that instance, it's going to be toothpaste. As a general rule of thumb, and this isn't always the case, guys, but it's a good rule of thumb, cleaning products, whether they are household cleaning products that you use to wipe your sides down and stuff, or whether it's soap, shower gel, toothpaste, these are all quite often of an alkali, alkali in nature. Now, we did have a purple question there. Are all acids dangerous? And then you can explain your answer. Hopefully, a lot of you had a go at that. The acids aren't all dangerous. I mean, fundamentally, acids are not all dangerous. As I've said, vinegar is an acid. And we throw that over our chips quite liberally. Another one that I would actively encourage you to eat as much as you can is vitamin C. Another name for vitamin C is ascorbic acid. If you ever drink fizzy drinks, you're drinking carboxylic acid. These are lots of substances that we consume on a regular basis actually contain acids in them. So not all acids are dangerous. It is much the danger of an acid is related to how strong or how concentrated that acid is. But we're going to be coming on to that throughout this lesson. So then, guys, so what we're going to be learning about today is acids, alkalis, and bases, and effectively how we measure them. And we're doing that because basically acids and alkalis and bases are fundamental aspects of chemistry. And actually, if you can understand acids and alkalis and bases, a large proportion of what you need to be able to understand in chemistry is built on that understanding. So the lesson's going to be running in a simple format. We're going to go through a few keywords. We're going to look at some of the indicators you may have come across before, maybe a few you haven't done, and the pH scale and how that relates to the amount of ions that are dissolved into a solution. And then we're going to compare concentrated and dilute and weak and strong. And those two things, whilst initially might sound like they're the same, actually in science they have separate meanings, and we're going to cover that during this lesson. And then finally we'll be looking at how we calculate the concentration of a solution, and then we'll end on a quick exit ticket as well, guys. So that's how the lesson is going to play out going forward. So initially, as I said, we're going to look at some keywords. For those of you that haven't been taught by me before, what I try to do is highlight when I would like you to take notes and put them into your books. You can do that throughout this lesson. If you choose to do so, you can be taking notes while I speak, but there are key parts of the lesson that I do need you to be putting into your notes. I will generally, unless I say otherwise, have included those, surrounded those by a red box. And you can see on the pack book we've got now a nice big red box surrounding our keywords of acids, bases and alkalis with their definitions. So an acid is something that contains a source of hydrogen ions. A base is something that contains a source of hydroxide ions, OH ions. And alkalis are soluble bases. Alkalis are a base that if you put it into water, it will dissolve. Okay, so pause the video now, guys. Quickly copy that down, and then we'll move on. Okay, guys, well done for getting those notes written down. These are key terms that you do need to be able to understand. Can you, looking at the information you've got on the screen in front of you, can you tell me which of these ions are polyatomic? Well done for having a go at that, guys. If you did have jot it down in your books or draw a line, what you can do is onto your notes that you've copied is you can actually say that the OH ion or the hydroxide ion is a polyatomic ion. What that term means is poly means there's more than one, and atomic means atom. So we can look at the hydrogen ions, that's formed of one hydrogen atom, whereas the hydroxide ions is formed of an oxygen atom and a hydrogen atom, and that's why it's a polyatomic ion. Okay, guys, so we're going to move on now, swiftly on. Now, you've probably seen this colour scheme before, this universal indicator chart before. You will have covered it in year 7, 8, 9, and now we're covering it again in year 10. It's really, really key for understanding pH, guys. This is the main indicator that can be used. It's a bit of a blunt instrument because it doesn't allow you to, say, calculate whether an acid has a pH of 3.456, but it will tell you the gross pH of that value. So in this instance, the color change, if you were looking at something that was a pH of 3, you'd get this lovely lime greeny color that you can see here. Or if something was a pH around 10, you'd get this nice deep blue color here. Now the pH scale works because of increasing relative concentration of hydrogen ions and or increasing hydroxide ions. Now these little blue arrow, these triangles that you can see on the bottom of the screen here, it relates to the concentration of, on the red triangle, it's hydrogen ions. So when we get down towards a pH of 0, you can see that the concentration of hydrogen ions compared to hydroxide ions is almost 100%, if not 100%. Whereas we jump down the other end of the scale, we get to a pH of 14, and we can see that the concentration of hydroxide ions, OH ions, are almost, if not completely, 100% at that point. Now, just to break that down a little bit, guys, as I've already explained to you, if something's got a large amount of hydrogen ions, a high concentration of hydrogen ions, it is acidic. And if it's got a high concentration of hydroxide ions, it is alkaline. Now, I'd like you to just pause the video for in a second and just answer these two questions and just think about what happens when you mix, you get an equal amount of hydrogen and hydroxide ions. And then what pH you think that substance may be. So pause the video, have a quick go at these two questions, and we'll go on after you've had a go. Okay, well done for having a go at that, guys. So when you mix hydrogen ions and hydroxide ions in equal proportions, you can see you've got one hydrogen here, you've got another hydrogen here and an oxygen. Hopefully that will have led you to understand that when you mix those two together, you're going to get H2O. H2O is, as we know, water. Okay, so there's two hydrogen atoms, one oxygen atom, mix them together, and we get water. And I hope, again, from the Do It Now that we did earlier and from years 7, 8 and 9, you guys are fully aware that not only is that the pH of water is 7. Okay, so well done for having a go at that, guys. We're now going to move on to the next part of the lesson. Now, we've got a range of different indicators. Now, as I said, universal indicator is the one that we almost universally use, hence the name. And that's because it will give you a range of values from 0 to 14, and you're able to, as I say, get a gross understanding of what that pH of that solution it would be. Now, we have other indicators, though. So the other indicators that you may not be as aware of is litmus would be the first one. So you might have litmus paper or a litmus solution, and these will turn deep blue in an alkaline solution, and they will turn red in an acid solution or acidic solution. So litmus paper is blue in alkaline, red in acidic. Methyl orange indicator will turn yellow in an alkali solution, whereas in an acidic solution, it will turn red. And phenolphthalein is the last of the indicators that we're going to be looking at today, will, if you place it into an alkaline solution, turn pink, whereas if you place it into an acidic solution, it remains colourless. You see no colour change. So what I'd like you to do, guys, is, again, these are key things that you need to be able to recall. Certainly, if you're a triple class, this is an absolute must for you to be able to recall. You do see this kind of question coming up quite frequently. You need to know these colour changes for acids and alkalis with these 3 other forms of indicator. So spend a few moments, guys, pop the video on hold, on pause, spend a few moments, guys, and copy this table down into your notes. Okay, guys, well done for getting that jotted down into your notes. It might be advisable if you've got coloured pens or highlighters or something to actually colour, put a blob of colour around where you put these words in, like we have done on this slide here. Not necessarily maybe colour the whole thing, but certainly add some colour into your diagrams. That does help you being able to recall these facts at a later point in time. So well done for copying that down, guys. We're going to now move on. We're just going to run through a quick series of questions. Basically, what I'm hoping you should be able to flow through these questions very, very easily. Most of this will be recapping from 7, 8 and 9. We've only got a couple of new bits of knowledge there that you'll be testing yourselves on. So there's 6 questions there. Pause the video, no more than 6 minutes, guys. You won't need any longer than that. Just have a quick go through these answers, and then we will pop up the answers after you've had a go at these questions. Okay, guys, well done. Well done for having a go at that. Hopefully you didn't find these questions too difficult. We're going to now quickly pop the answers up on the screen. So place the following pH values of increasing acidity, and they go from 4, 1, 7, 9, and 6. So if we value them of increasing acidity, we have to start with the least acidic first, and that gives us 9, 7, 6, 4, and then the most acidic is 1. Now, what iron is present in acidic substances? We've already mentioned it a few times, guys, when we were looking at the universal indicator scale. And so hopefully you guys will have all popped down that it is a hydrogen ion that is present in acidic substances. What is an alkali? Now, this was one of the key terms that we had back at the top end of the lesson. So an alkali, as we should know, guys, is a soluble base. This is a base that dissolves in water. And if we can remember, a base is something that can dissociate or release, provide, supply hydroxide ions. That's OH ions. So what colour would a solution of that's pH of 12 go if we were to place some phenolphthalein into it? And that solution would turn pink. So remember, that was the colour change that you needed to recall for phenolphthalein. Now, litmus paper, if you guys can remember, that went blue. And then universal indicator, this is one that you should know anyway. This is one you should have learned. But as I say, over the last few years on a number of occasions, and that will turn a deep purple colour. It's quite an alkaline solution, a pH of 12 is. Okay, well done for having a go at that. I don't know why I've left the purple question back up on this question, because I think we did cover that in quite a bit of detail back at the very beginning of the lesson. So, concentrated versus dilutes. Now, I don't know about you, but when I was a young lad, my parents always used to make my squashes look like this. Very, very dilute drinks with very little squash in there and an awful lot of water. I remember going to my cousin's house, and actually my auntie and uncle made their squashes a bit like this, and I didn't know quite what had happened when I had a mouthful of that squash. Because this is a higher concentrated solution, there were so many more molecules of squash in the drink that I was drinking. My tongue went into meltdown. I had never tasted something so sweet before. So what I'd like you to do, guys, sorry, I'm going off on a tangent. What I'd like you to do from this slide is basically have a look at those series of starting at quite a dilute solution, moving through to a more concentrated solution. I'd like you to see if you can create your own definitions for dilute and concentrated. Now, I will give you a bit of a heads up, guys. Please do not use the words weak or strong, okay? They have different meanings in science. So please try to avoid using those terms, but pause the video now, see if you can come up with your own definitions, and I'll provide you with some afterwards, and you may need to change the ones you've come up with, but have a go, and we'll see if we need to correct our answers afterwards. So pause the video now and come up with a definition for dilute and a definition for concentrated. Okay, well done for having a go at that, guys. So here's my definitions for, well, they're not just my definitions, they're also the examining board's definitions. So these are the good ones to be able to recall if you are ever in an exam situation, you've got a question based around this topic. So a concentrated solution is a solution that contains a large amount of solute dissolved into the solution. So what I mean by that is a large amount of solute. This juice here and a dilute, we'll do the definitions entirely. So a dilute solution is one that contains a small amount of solute dissolved into the solution. So a dilute solution here, you can imagine this probably got filled up to about here with squash and then the rest of it water. So we had very, very small amounts of solute, which would have been the neat squash. And then the whole solution is once you mixed it in with the water as well. Whereas here, we would have had maybe a little bit more squash and then the rest water. By the time we got to here, we're probably having almost half of this glass would have been squash and then the rest of it would have been water. So this has a much larger amount of solute, which is the neat squash, and the solution dissolved into the solution as the whole glass. So a concentrated solution is a large amount of solute dissolved into a solution, while a dilute solution is a small amount of solute dissolved into a solution. Well done for having that going, guys. Make sure you've corrected your answers, and as I say, you've avoided to use the words weak or strong. Certainly when we're dealing with acids and alkalis, those terms have very, very different meanings. Okay, so a concentrated acid. A concentrated acid contains a large mass of acid dissolved in a given volume of solution. A dilute acid, however, contains a smaller mass of acid dissolved into a given volume of solution. Now, I know it's pretty difficult to see on these two squares we've got here and here, but there's actually the same amount of water molecules. These little white dots here are the water molecules in this solution, and in this instance, the green dots are the acid that we've got in here. And we've got many, many, many more acid molecules in this box than we do have in this box. So there's a large mass of acid that's been dissolved into this solution. And on this one, there's a smaller mass of acid dissolved into the solution. Now, as I said, guys, I've got a couple of red boxes for you there. please pause the video, have a go copying these statements down into your books. If it's the kind of thing that you find helpful for your notes, then also have a go representing it in the same way with these diagrams that we've got here and here. If you do that, try to make sure that you have quite a clear, evident difference in the amount of acid that has been dissolved into the solution. The amount of green balls that you would put in your diagram must be much higher on this concentrated side than it is on this dilute side. Okay, so pause the video, have a go at that, guys, and when you come back, we'll move on to the next slide. Okay, well done, guys. Well done for having a go at that. So we are now going to move on, and we're going to be looking at the concentration of hydrogen ions and how that is linked to the pH of a solution. Now, the pH scale is what we refer to as a logarithmic scale. Now, without going into any massive maths details or overburdening you with that, what that basically means is every time the pH scale jumps by 1, it's actually a change in the concentration of, if we're becoming acidic, in hydrogen ions by a factor of 10. So a solution that has a pH of 7, we're going to throw some arbitrary numbers into it. Let's just say the pH of the solution, pH 7, this solution has 10 hydrogen ions in it. That's not the case, but we'll just say that for this instance. Something that has a pH of 6 has 10 times that amount of hydrogen ions. So if it was 10 here, it's now 100 here. And then if following the same principle, if that pH value drops down to 5, what was 10, then 100 is now 1,000 times the amount of hydrogen ions. And then going from, so we got one jump there, that's 10 times different. From 6 to 5, that would be 100 times different. And then when we get to 4, that would be the 1,000 times different. Sorry, guys, I'm tying myself up in knots with numbers. So basically what you need to be able to understand is that for every jump that we have on the pH scale, the concentration of hydrogen ions increases by a factor of 10. It actually works the same way in reverse. This could be OH ions, hydroxide ions. We could be talking about an increase in the alkalinity of a solution, and this number could be going up. So if we were looking at a pH of 8, it would have 10 times the amount of hydroxide ions in it. So the scale works the same in both directions. But what is, as I say, really key for you guys to be able to understand at this point is that for every jump, the pH scale, we see an increase by a factor of 10 in the concentration of hydrogen ions. Okay, guys, so now I've explained that to you, what I'd like you to do is just have a go at copying this table into your notes. And whilst you're copying your table into your notes, just see if you can add the values that we've got missing from this table. So copy and complete this table into your notes, pause the video, take as long as you need, guys, and when you come back, we'll go through the answers. Okay, well done, guys. You've done really well at this so far. We're cracking on through this lesson at a lovely rate. So hopefully you've copied this into your worksheet. The really diligent ones amongst you will have used a ruler to draw all your lines, because you know in science that is quite an important thing to be doing. I'm not going to be able to even see the work you're doing, so I can't necessarily judge whether you've used a ruler. But when drawing tables, it is always advisable to use a ruler. Makes it much neater and tidier. But in any case, in answer to these missing squares, because this value here, this is our first value that we have on this scale. We've got 3 blanks and then a value here. We know that this value is 10 times smaller than this value. So if we were to divide this number by 10, we would get 0.001. All I've done is add a 0 in there. If you're dividing something by 10, that's quite an easy way of being able to do it. Now, we've done that this once here. we're going to do the same again, make the same jump. So it's another factor, is 10 times smaller. So it's another division by 10, and that gives us 0.001. Now, the last of the relative concentration of hydrogen ions we're going to be looking at, we've got yet another jump of 10. And so that's going to be 0.00001 as a relative concentration of the hydrogen ions. Okay, so hopefully you guys have been able to suss that out and got that written down. We're now going to move down to the bottom of this table and look at the pH of the solution. We've got a value here of 1. Now, that means we know that going this way, we've got a factor jump of 10. That's going to be 1 whole pH unit lower. So that gives us a pH unit of 0. And then we know from this side to this side, we've got another jump of 10. I don't know why this arrow and 10 is a little bit off kilter, but we've got another jump of 10. So we know that that's just another jump up the pH scale from 1 to 2. And again, another jump of 10 here, guys. So 3 becomes 4. And then this 4 here, another jump of 10 pH. So what we're really, really highlighting here, guys, is that for every jump of 10, the pH becomes more and more acidic. Okay, well done for having a go at that, guys. We're cracking through it at a lovely rate here. So we're going to move on to the next slide. So, as I said earlier, when we were talking about weak and when we were talking about concentrated and dilute solutions, and how the terms strong and weak can't really be used in their definitions. And that's because we have strong acids and weak acids, and it doesn't matter how, it's not relative to how concentrated they are just purely strong acids or weak acids. Okay, so in a strong acid, we can see on our diagram here, a strong acid is one that completely dissociates. So an acid, an acidic molecule will have, in this instance, we've got the hydrochloric acid, which is a hydrogen and a chlorine molecule. And in a strong acid, these molecules completely dissociate. So the entirety of the acid becomes ionic, and you end up with lots of hydrogen ions, and in this case also lots of chloride ions. So in a weak acid, something like we've got here, ethanoic acid, that dissociates partially. So a weak acid will only partially dissociate. So only a few of the ethanoic acid molecules will actually split up and become ionic. And in this instance, you end up with, I dread to think, I can't even think what that's what that part of. I can't give you a name for that, I'm afraid, guys. But you end up, if you look at the diagrams, that might help explain it a little bit better. In this diagram, each of these circles is a hydrogen ion, and each of these circles is a chlorine ion, and they have become completely separated. So they are two separate ions. Now, if we go over to the weak acid, we've got each of these clear oval shapes represents an entire ethanoic acid molecule. So we can see we've got loads of ethanoic acid here. This could be quite a concentrated solution of ethanoic acid, but because it is a weak acid, only one of the molecules in this bundle of molecules has actually disassociated and become a hydrogen ion and a negatively charged ethanoic acid ion. So what we ended up with is just one hydrogen ion here, one of these over here, and the rest of these are undisassociated. So these are all complete ethanoic acid molecules, and that means because they're only able to donate one hydrogen ion, it's a very weak acid. So again, guys, you're probably knowing what I'm going to say now. We've got a couple of red boxes. Again, these are really important terms that you do need to be able to understand the distinction between them, between concentrated and dilute and strong and weak, certainly when we're looking at things talking about acids and alkalis and bases and the like. So red boxes, guys, you know what I'm going to say. You need to pause the video, copy those down. Again, if you wanted to, if you find that you remember stuff better by drawing out and having visual representations, then please feel free to take the time to copy these diagrams down. What I will say is, if you do copy these diagrams down, what is key for these diagrams, and I say that as an intended or an unintended pun, is that you include the key for the diagram. So you need to be including the fact that the white clear circles, or whatever color, however you represent them, represent the hydrogen ions. The big green ones represent the chloride ions, whereas over this side, the clear ones represent the entire ethanoic acid molecule, and it's these red ones that you can see here and here that are represented the dissociated ions, and it's this little hydrogen one down here that's deriving the pH of this solution. Okay, guys, pause the video, get those copied down, and we'll move on to the next part of the lesson. Okay, well done, guys. We're doing really well. We're getting there. Not too much more to go. So we're going to move on, and we're going to be looking at concentrated versus dilute solution, but it's actually also really looking at how we can calculate how concentrated a solution is. Now, I actually, this equation that you can see on the screen in front of you was actually, you know, for one aspect of my job as a marine biologist, was part of my bread and butter. Now, when I was regularly having to treat marine animals, fish and the like, I would have to treat them with a medication to a specific amount, and we would often get that medication arrive as a powder, and I would have to add water to it, then know the precise concentration of that solution that I could then take out enough of the medication into a syringe and inject it into an animal. So I use this equation a lot as a professional marine biologist. It's a really useful equation. And you know what I'm going to say, guys, I've covered it in a red box. I've actually got a number of different things that have been covered in a red box here, guys. These are all really key things for you to be able to understand. Now, firstly, your concentration equation, vital. You really do need to be able to recall that, guys. Sometimes in exams, they will give you the equation, but quite often they won't. So make sure that you are able to recall that equation. It's quite straightforward when you think about it. The concentration of something is equal to how much you've got that you're putting into something and how much of the solution that you're putting it into. I mean, it's quite straightforward, really, but make sure that you're able to recall that equation. Also, when we talk about concentration, we use a unit. I don't know if it's a unit that you will have come across, but we use grams per decimeter cubed. Now, when you look, I've got a red box around both of these, so I will give you a chance to pause it in a second and record it. This minus sign that you can see next to this this 3 here, this cubed unit here, is only there because we have removed the dividing sign between the grams and decimeters. If you were to put this dividing sign in at this point, you would be able to remove that minus sign. If you don't put the dividing sign in at this point, then you would have to add that minus sign. If you're a triple class, this is how I expect you to be presented, grams per decimeter cubed. And actually, I mean, that's true of any kind of a unit where you have a dividing sign part way through. I would expect, again, this kind of minus sign being added in. The cubed is essential, though. That 3 number does relate to this decimeter. The minus sign just relates to the fact that there is no divide sign. Okay, guys, so there is a question on this page at the script slide as well, but what I'm going to get you to do is I'm just going to give you a few moments first off to copy those red boxes down. I'll just also mention that 1 decimeter cubed is the same volume as 1 litre or 1,000 centimeters cubed, or 1,000 milliliters for that matter. 1,000 milliliters equals a meter. 1,000 centimeters cubed also equals a milliliter, and 1 decimeter cubed equals both 1 litre and 1,000 centimeters cubed and 1,000 milliliters. So copy those red boxes down, guys, and then we'll have a go at working our way through the example question that we've got on the slide. Pause the video, get them copied down, and we'll come back to me when you've got it done. Okay, guys, well done. We're really cracking on with this lesson now. We're getting on really well. So, for example, we've got a question here. If 4 grams is dissolved into 50 centimeters cubed, what would the concentration be? Well, we know that 4 grams goes in on this top line of the equation here. That's the amount that's being dissolved. So we can have 4 at the top there. The unit is in grams, and we've got grams on our unit for concentration. So we don't have to do anything to this number. It's dissolved into a volume of solution of 50 centimeters cubed. Now, that does pose us a problem because, as we've just discussed, we need to be having our units of concentration in decimeters cubed. Centimeters cubed is not decimeters cubed. And what we have to do to this number to ensure that it's the correct number is we first of all have to divide it by 1,000. So 50 divided by 1,000 will give us 0.05. So that would be 0.05. Sorry, I've been hideously bad there and not put decimeters cubed on the back end of that 0.05, but that would be the unit that we would be looking at. So now we've got all of this information that we've got. What we should be able to do, we know we've got 4 grams up here. We know we're dividing that by 0.05. And were we to calculate that question out entirely, we would get 80 grams per decimeter cubed. So hopefully, guys, you were able to follow that route through that equation, and you were able to insert the values in the right locations. And I really hope you were able to do that, because I'm going to be really mean now, and I'm going to leave you to your own devices to have a go at these 4 questions. Now, remember, I do expect, especially if you're a triple class, but I really do expect the appropriate units to be put into your answers. I'm a bit of a stickler for this. You have to, a number in science has virtually no meaning or value whatsoever unless you attach a unit to it. If you just put the number 4.56, I don't know whether you're talking about elephants. I don't know whether you're talking about giraffes. I don't know whether you're talking about the number of miles you walk to school. I don't know. I need to have a unit attached to that value, to that number. And at that point, then I understand entirely what that number means. Sorry. Sorry, guys. So if you can now pause the video, guys, there's 4 quick questions to have a go at. And then when you come back, we'll go through the answers. Okay, well done, guys. Hopefully you didn't find these questions too challenging. We'll jump straight in with going through the answers. So we know that we have got 12.5 grams of hydrochloric acid. That's being dissolved into 0.4 decimeters cubed of water. So we know that we have an equation that should be looking 12.5 divided by 0.4. This is already in decimeters cubed, guys, so we don't need to do anything about the units. And see, what I've done here is there's the answer. It's 31.25 grams per decimeter cubed. Now, I've gone back to the old style of writing this in, and I've taken the minus figure out and I've put the divide sign there. Either that way or without the divide sign and the minus sign in there, either of those would be totally accurate and totally acceptable in an exam or in any work that I was marking. So well done if you got that right, guys. The next question. Now, the next question is 30 grams of nitric acid is dissolved in 0.7 litres of water. Now, we are at a bit of a problem here, guys, because we are using different units. You can see we've got 0.7 litres of water, but we need it to be in decimeters cubed. But if you can remember back from the previous slide, 1 decimeter cubed equals 1 litre of water. So in this instance, there's no mathematical wrangling of the number 0.7 that we need to do. We can still just insert it straight into our equation. And when we do that, 30 divided by 0.7 will give us 42.86. You will probably find that you maybe had 42.857. I've done the appropriate rounding on that equation, on that answer. But again, we've got 42.86 grams per decimeter cubed. And if you've taken away this dividing sign and put a minus in front of that 3 there, that's as accurate as you can see on the board in front of you. So the next question is 22 grams of nitric acid is then inserted into, or is it placed into 0.2 litres of water. Now, again, exactly the same as before, guys. The 0.2 litres of water is equivalent to 0.2 decimeters cubed. So we don't have to play around with this number at all. And we can just input the value straight into our equation. And that will give us our concentration of nitric acid as being 22 divided by 0.2 equals 110 grams per decimeter cubed. So well done if we've got those ones right, guys. So this last question was a bit of a stickler. Hopefully we went through this technique on the last slide well enough for you all to have been able to have a go at it. But it is a little bit more tricky because we do have a volume of our solution being recorded in centimeters cubed. It's no longer in liters, it's not in decimeters cubed, it's in centimeters cubed. And that means, if you can remember correctly, that what we had to do was divide that number by 1,000. So once we've divided it by 1,000, that will give us a value of 0.2. So we've got all of the numbers, we add them into our equation. 18 divided by 0.2 is equal to 90 grams per decimeter cubed. So well done if you managed to get all of those correct, guys. A really important equation for you to be able to work out. And as I say, as a professional marine biologist, it was an equation that I used on a regular basis. It really is a useful equation to be able to recall. So well done for having a go at that. We're going to now move on, guys, and you're going to be really happy to know that we have now just got an exit ticket to work through. And then once you've done that, you've stuck with me to the end. You've done really well. And yeah, I'm really impressed with the with your ability to stick with it this long. So, guys, the exit ticket. 5 questions. It's the same principle that you would have been used to when you were in class. Pause the video, give yourselves a few minutes. These are all questions that if you needed to, you could look back through the notes you've made. Ideally, what I would like you to do is not be looking through those notes. Turn your notes over and see if you can answer them from memory. If you struggle to answer them from memory, then by all means, please go back through your notes. Make sure that you've got the right answers down. We will go through the answers once you've had a go at them, and that will be the end of our lesson. So pause the video now, guys. Have a go at these 5 questions, and we'll see where we get afterwards. Okay, guys, well done for having a go. This is, as I say, the last few moments of the lesson. We're just going to quickly spin through these answers and make sure you've got the correct ones. So if a pH of a solution has dropped from 7 to 5, how many times has the relative concentration of hydrogen ions increased by? Now, remember we said that for every single unit, every single pH unit that is dropped, that is a factor of 10 times more hydrogen ions. So we can say that it's dropped by 2, that's 10 times 10, that's 100 times more 100 times more hydrogen ions in that solution. Now, can you define a strong acid? Hopefully, guys, you were able to recall that a strong acid, not a concentrated acid, but a strong acid is one that will completely disassociate into ions when it is dissolved in water. What color will milfoil orange indicator turn in an alkaline solution? Now, if you remember, guys, that was yellow. Methyl orange indicator goes red in an acid, but in an alkaline solution, it goes yellow. What is the difference between an alkali and a base? Now, there is a very subtle difference, and that is an alkali is a soluble base. So an alkali is a type of base, and it is a type of base that will dissolve in water. So that's the difference between an alkali and a base. An alkali is a base, it's a type of base, it's a soluble base that will dissolve in water. And what is the pH? What is the pH if the relative amounts of hydrogen and hydroxide ions are equal? Hopefully, guys, you can remember back to that slide where I had those two triangles, the red and the blue triangle, and we were discussing about the relative concentrations of hydrogen and hydroxide ions. And you can know that when you combine, when you've got equal numbers, they kind of neutralize one another. They have a neutral pH, or that is also known as a pH of 7. Okay, guys, well done for sticking with me. I'm really, really chuffed and impressed you got this far. With a bit of luck, well done for getting this far. I look forward to seeing you at some point in time. I think the next recorded lesson or next live lesson will, for you guys will be delivered by me will be sometime next week. So I look forward to seeing you guys next week. I hope you're able to get on and access all the different learnings that that you've been charged with across the different subjects. If you are struggling to get onto either Teams or to class charts or to Seneca, then your parents should have by now been sent out a log-on details for all 3 of those systems. But if you are having difficulties, if you email myself or your form tutor, we will, as teaching staff, we will be able to assist you and help you access this online learning. Well done for having a go, guys. I look forward to giving you a lesson next week, and I hope you have a lovely week. Take care and all the best.